the problems. I'll probably just go back and record those later. All right, so good. All right, so that was number 54. So now I want to go down and do number 60. All right, so it says, which of the following aqueous solutions would have the lowest vapor pressure? Okay, so we need to think about, how vapor pressure is affected. Well, once again, it's just based on the amount of solute that's dissolved in the solvent, okay? And also we have to take into account the number of particles. And so something, we've done before is we've just thought about how many particles these solutes break up into when they are dissolved, okay? So again, this breaks apart into the sodium ion and the chloride ion. So it has a value of the Van 't Hoff factor, or the number of particles. You can think of it either way. Okay, it's 2 for sodium chloride. And we've seen this one before. It's going to be 3 for the magnesium chloride, because it breaks apart into 1 magnesium ion and 2 chloride ions. Okay, so this is methanol. This is a non-electrolyte. And that's kind of a memorization thing back from Unit 3. Okay, did I spell that right? Yeah, I think so. So that's just has a value of 1 because it stays just in that form. It doesn't ionize at all. So it doesn't produce more particles when it's dissolved in water. It just stays together as that one molecule, whether it's dissolved or not. Okay, and then the lithium phosphate, well, that's going to give us 3 lithium ions. If you just look at the formula, subscript 3 means that there's 3 of these lithium ions for every unit of lithium phosphate. And there's going to be 1 phosphate 3- ion, okay? And so that's a total of 4 particles. Okay, so the total, the concentration of particles is just going to be this number times its molarity, which is given. So this would be like 0.30, and this would be 0.1, so 0.2, 0.30, because 3 times 0.1 is 0.3. This one would be 0.30, okay, and this one would be 0.40, okay? So that's the one that looks like it has the highest concentration of particles that are dissolved. So that's going to be the one that affects the vapor pressure the most. And remember that the effects are that when you dissolve a solute in a solvent, what you do is you elevate the boiling point, you lower the freezing point, and you lower the vapor pressure, okay? And so the one with the lowest vapor pressure is going to be the one that's affected most by the presence of a solute. And that's going to be, in this case, the lithium phosphate, the one with the highest concentration of particles, okay? Now, and I pointed out in detail like that because you have to pay attention to the wording. What if it had said, which of the following aqueous solutions would have the highest vapor pressure? Well, the highest vapor pressure would be the one that's least affected. So it would be the one with the smallest concentration of particles. You see what I mean? So you still have to pay attention to the wording of the question. Is it asking you to pick the one that's most affected, lowest vapor pressure, or the lowest freezing point, or the highest boiling point? Or is it asking you to pick out the one that is least affected? So in that case, it would be the lowest boiling point, the highest freezing point, or the highest vapor pressure. So pay careful attention to the wording of these type questions. There's some potential curveballs in there. All right, how are we doing on time? We're doing good on time. So let's go back to the assignment here. All right, so that was number 60, right? Okay, so now let's look at 61. Okay. All right, so this is 61. So this is a question that involves something we call Raoult's law, okay? And Raoult's law is very similar to an equation we gave you when we were talking about Dalton's law back in Unit 3. And so, yeah, I think it was Unit 3. Unit 3 or Unit 4. I do get them confused sometimes, I apologize, but you'll recognize this when I I'm gonna write it out. So the P, and in this case, P stands for vapor pressure. So the vapor pressure of the solution, it's equal to the mole fraction of the solvent times the vapor pressure of a pure solvent at the given temperature, okay? And that's really all this is asking you to do, is to use this equation. So a non-volatile solute is dissolved in benzene, and the resulting solution has a vapor pressure of 18.5. Okay, so the resulting solution has a vapor pressure of 18.5. So that means that this one is 18.5 torr, okay? The vapor pressure of the solution. What is the mole fraction of the solute? Okay, so there's the important word. So the mole fraction of the solvent, we don't know, but I do know the vapor pressure of pure benzene at that whatever temperature. These are specific to temperature. It's just the temperature is not listed in this particular problem statement, but it's 26.5 torr. Okay, so the first thing I need to do is I need to rearrange and solve for the mole fraction of the solvent. Okay, and so that's just the 18.5 divided by 26.5. So 18.5 divided by 26.5. And so that's 0.698, we'll say. Okay, so that's 0.698. All right, so remember that this is a mole fraction, right? So this plus something has to equal 1, right? And this, since this is the mole fraction of the solvent, then that is the mole fraction of the solute, which is what we are what we're trying to find. So 1 minus 0.698 is what we need to do to find that. So 1 minus my answer is 0.302 with rounding. Okay. I think that's the correct answer. So let me just plug it in, make sure. All right, oops, 302. I'll clear all that away. See if I'm right. Yeah, okay. So again, you just use Raoult's law. You plug in the numbers that you know, the vapor pressure of the solution, the vapor pressure of pure benzene. Oh, yeah, well, this is kind of another route, but it just shows you calculating it slightly differently than what I did, but you get to the same answer. And it's not all that different than what I did. All right. Okay, so let's see, that was number 61. So since we do have some time, let me do 66. Yeah, all right, so I wanted to do a couple of questions about, I don't know if you remember, but in one of those lessons, I asked you to do a little bit of independent learning. I asked you to look up the definitions and sort of understand the concepts behind surface tension, viscosity, and capillary action. And so I wanted to do just a couple questions on, those topics, just to kind of to help you to understand what I really want you to know about those three properties. So for example, so what are the factors, which of the factors contributes to a low viscosity of a liquid? Well, remember that viscosity ultimately means resistance to flow. Resistance to flow, okay? And so something that has a high viscosity means that there's that's a lot of resistance. Okay, so it would be something like, something like syrup, maple syrup, or something like that, something that's very thick, a thick liquid, okay? And so some of the factors that go into making something a very viscous liquid, if it has a high boiling point, then that's something that's typical of a highly viscous liquid, okay? So that's, not gonna contribute to a low viscosity. If it has a high boiling point, then that's gonna be a property that I would expect from a very thick, a very viscous liquid. Hydrogen bonding also leads to a high boiling point, right? Those two things usually go together, so I can kind of eliminate that one. And also the hydrogen bonding is those are very strong intermolecular forces, right? Those are very strong intermolecular forces. And so they're going to want to hold those those liquid molecules, to not necessarily a solvent, but those liquid molecules together. And so that's going to give you some resistance to flow. Okay. A low temperature, obviously the old saying that it's like molasses in January, right? You've heard that probably before. So something very thick like molasses is even slower when it's cold. So I can eliminate that one. And then a high molar mass, also that's usually something that goes into being a very viscous liquid, like motor oil. Motor oil are these, it's a hydrocarbon with a lot of, like a very large carbon straight chain. So for example, it might be something with 20 carbons in it, so it's like 20 carbons in a chain. So, lots of carbons in a long chain. And so again, that makes for a very viscous liquid. So it's this one kind of by process of elimination, but also we can kind of point out something. So let's say that I have this, molecule where all the carbons are in kind of a straight chain, like kind of like a string of spaghetti. But if I change those arrangements of the carbons so that they're kind of in a ring or in a more compact structure, and we talked about this in a different lesson. We talked about branching versus the straight chain. Remember the lasagna noodles versus the billiard balls example? So that affects the viscosity also. So it's easier for these guys to flow past each other than for these guys, because again, lasagna noodles versus the billiard balls. This is like the lasagna noodle where the intermolecular forces, if I have another one of these, there's a lot of area, a lot of opportunities for those intermolecular forces to exert themselves, okay? So that leads to a higher viscosity, okay? But if you have these compact structures, then like the billiard balls, there's not much contact, right? So there's just fewer opportunities for those intermolecular forces to exert themselves, okay? And so that leads to a low viscosity. Okay. Okay, so that's the one I'm going to select, the compact molecular shape. And so, again, if you need to go back and review that lesson, I think it was maybe lesson 1, where the amount of branching impacts the intermolecular forces. And in this case, what we're saying is the higher the intermolecular forces, the more intermolecular forces, the more viscous the liquid. Okay. All right, so let me clear all that away. Select that one. Show the answer. Okay, there we go. All right, so let's see how we're doing on time. We've got time for one more. Okay, so the last one I wanted to do is 67. And again, it's similar. It's about viscosity. So based on what we just discussed in the previous question, which of the following would exhibit the highest viscosity? And so essentially what we know now is that we're looking for the one with the highest intermolecular forces. Okay, and so think about what intermolecular forces these different molecules have. This one, because it has the oxygen-hydrogen connections, right? This one has hydrogen bonding, so it has H bonds. Okay, and it's a polar molecule, so it also has the dipole-dipole intermolecular forces, and everything has the London dispersion forces. Okay, so this is a good candidate for the one with the highest viscosity because it seems to have a relatively large amount of intermolecular forces. Okay, this one has no oxygen-hydrogen bonds, or no oxygen-hydrogen connections. These hydrogens are all connected to the carbons, right? And so this one cannot have hydrogen bonds, but it is a polar molecule because it has, it's a carbon and hydrogen containing molecule with an oxygen. So that means it's going to be polar. So it's going to have the dipole-dipole, and then everything has London dispersion forces, all right? So this one has hydrogen bonding because it has the oxygen-hydrogen connections there. Okay, and it's polar, so it's going to be dipole-dipole, and also everything has London dispersion, okay? But if I'm going to compare this one, A and C, I'm not going to choose C because A is also a higher molar mass. It's larger. The molar mass of A is larger than the molar mass of C. So these guys, A and C, both have the same intermolecular forces. but because A has a higher molar mass, I think this is the one that's going to lead to a higher viscosity. Once again, going down here, these guys don't have hydrogen bonding, right? These hydrogens are only connected to carbons. This is a polar molecule, so it will have dipole-dipole. Okay, and of course, London dispersion forces. Same thing here. The structure for this one is polar. It's got a polar, it's a polar molecule because here's going to be the partial negative area of the molecule, and here's going to be the partial positive area of the molecule because of the electronegativity differences, right? The bonds over the overall dipole is going to point towards the chlorines because these are the most electronegative elements. All right. And like I said, if you do the symmetry type test, if you cut that molecule, it's different on one side than on the other. So since there is some asymmetry, it means it's going to be a polar molecule. All right. So it does have the dipole-dipole, pardon me, it does have dipole-dipole. And everything has London dispersion forces. But again, I can eliminate them because these guys already have the hydrogen bonding. And I can choose A over C because this one has a higher molar mass. Okay, so this is a good question for just, testing. Do you understand and can you identify all of the molecular forces that are present? And do you understand the relative strengths of the intermolecular forces and things like that? So if you understood, everything I've said or on your own, all of the factors involved in this one, you're probably pretty strong on your lesson 1 topics there. Oops. So I'm going to choose A. Okay. All right. Yeah. Stronger intermolecular forces, higher viscosities. Okay. All right. So that is all of the questions that I wanted to go over. So I'll just pause a minute. And if anybody has a question from the homework assignment or the review problem set that they want me to go over, now would be the time to either take yourself off mute and let me know, or you can put it in the chat box and I'll see it. And again, don't hesitate to contact me outside of class too if you want to do it that way. I can, try and reply in an email, or we can set up a Zoom meeting or something like that.
Did you mention if there is going to be a final exam for the regular chem class?
Oh yeah, there's going to be a final exam. So let me, I'll end. You know what? Because I forgot to start recording at the beginning, I'm actually glad you mentioned that. So now I can just bring up the share that I had with all that administrative information. I don't know if you saw this. Christine, did you see this slide? Were you?
No, I was a little late.
Yeah, no worries, no worries. You weren't the only one, so that's no problem. So this is my announcement kind of things. And I guess it doesn't really say anything about the final exam on here, but yes, we're going to have a final. I will talk more about that on Friday. What I did say about the final is that there is an assignment in Blackboard, you'll notice, called the 140 student assessment. Okay, it is a mandatory assignment. It's used by the university to assess the effectiveness of instruction in all Chem 140 classes. So not only you guys, but everybody that's taking Chem 140 will be taking this assignment in Blackboard. And so it is mandatory, so I'm incentivizing it in 2 ways. So first of all, it's going to be, points that contribute to your overall grade, but also whatever points you earn on this assignment, I'm going to add those to your final exam score. Okay, so it's kind of like it's a twofer. You have this assignment that you take, but also it's an opportunity to earn some bonus points on your final. So the final exam, I'll talk more about the details regarding that on Friday. I'll also send out an announcement, I'm sure, with some of the details too. But one thing I can tell you is that I'll open it up for people to start taking on Monday morning, and I'll give you until Thursday, either Thursday evening or Thursday afternoon to get it done. And then there's these other important announcements also to keep in mind. Is that okay, Christine, or do you have any other, specific questions about it that I can answer now? Or
no, that's good. I was just wondering when it was going to be available.
Yeah, it'll be on Monday morning. The Unit 7 quiz will be available this afternoon, but the final won't be available until Monday morning. Okay, anybody else? Let me look at my chat box one more time. It always disappears on me. All right, so I see question 17 in the Unit 7 review. Unit 7 homework. Okay, so if anybody wants to cut out, you can. I know we're getting close to the end, but I will go do that one. So let me find that and then I'll share it as soon as I get to the right assignment. Okay. Okay, so we'll stop that share and we'll share this screen. Okay, so, all right, Caleb, is this the right one? You want to hit me on the chat box? I think this is the one you're talking about, right? Number 17 in the homework assignment. Yes, okay, good. All right, so which one of the following aqueous solutions would have the highest freezing point? All right, so remember, this is exactly what I was talking about earlier, that the wording is important. So remember that when we dissolve a solute, in a solvent, three things happen. First of all, the boiling point goes up and the freezing point goes down and the vapor pressure goes down. Okay, so when this says the highest freezing point, what it's talking about is the one that affects the solvent the least. Okay, so you do have to pay attention to it. So we do need to take into account the number of particles that this breaks apart into. So sodium nitrate, you get the sodium ion and you get the nitrate ion. So it breaks apart into 2 particles. This is methanol, it just stays methanol. So it stays as 1 particle. This is a glucose, this is a sugar molecule, so it also just stays C6H12O. Let me just be professional about it and erase all that stuff. So it just stays in that same form, C6H12O6. So it just stays as 1 particle. And then the calcium chloride breaks apart into a calcium 2+ ion and 2 chloride ions. So it breaks apart into 3 particles. And so the sort of the effective concentration, or the concentration of particles, would just be this number multiplied by that number. So 2.0 molal, 1 times 2 is 2.0 molal, 1 times 1 would be 1.0 molal, and this is 3 times 1, so that would be 3.0 molal. All right, so now you want to pick this one because it's the lowest concentration, because that's going to affect the solvent's properties the least. All right, so I'm going to I think that it is this one. Let's see if I'm right. Correct. Okay. All right, anybody else? Any other questions you want me to hit real quick? Going once, going twice. All right. Okay, well, thanks everybody. Thanks for hanging in there. And again, we'll meet together on Friday where, among other things, we'll probably focus on Friday on some information about the final. And then if you have any questions from the review assignment, the full semester review assignment, I can go over those. And if you don't, then we'll have some practice kind of questions, just reviewing the semester as a whole. All right, everybody have a great day. We will see you on Friday.